Welcome, ladies and gentlemen. So let's go ahead and take the particle's acceleration function and see if we can, and initial velocity condition, and see if we can determine key things like how far did the particle travel, right? What's the displacement of the particle over the time interval t equals 0 to 2 seconds? And we can do this analytically. So again, first step, we'll do strictly pencil and paper. How would I determine my velocity function given acceleration? Easy cheesy. We know our velocity function v of t is given by the antiderivative of acceleration a of t. So go ahead and tell us term by term what that would look like. Kobe?
T squared plus 3t minus 4.
Hang on, slow down.
Plus.
Let me do a plus c first. And then how are you getting the value of c?
So you can put 0t in that's equal to 4.
Awesome. So if we evaluate my velocity function when t equals 0, it has to equal -4, and that gives us the constant. So the only way for this to happen, 0, 0, 0. C has to be -4, which means that when I go through and do my displacement and distance travel calculations, I'll be starting with the velocity function that I now have pinned down as v of t equals t squared plus 3t minus 4. At this time, I'd ask that you raise your hand if you had the same velocity function as Kobe. Very good. Yes, let's use it to get displacement. So in general, I know the displacement of a particle over an interval a to b is given by the integral of my velocity function v of t over the same interval. For us, that would be the integral from 0 to 2 of v of t with respect to time. Because I've called v of t, right, I don't have to write that necessarily in there, but I am going to have to generate an antiderivative function symbolically in order to evaluate this. So let's do it. Ready? An antiderivative function for velocity would be what, Courtney?
1/3 cubed plus 3
Awesome. And we can evaluate that from my lower limit right to my upper limit by plugging in that upper limit all the way through in accordance with the theorem of calculus. Plugging the lower limit all the way through, working it out and subtracting. So let's do it. Ready, go. 2 in for t, 8/3 plus 2 in for t, 3/4, 12, 12 over 2, 6. Is that right? 4 times 3 is 12 over 2 is 6. I get 6 again. Minus 8. So I get 8/3 plus 6 minus 8 is 8/3 minus 2, and 8/3 minus 6/3 is 2/3. So I get 2/3. Right here, get 2/3. Hey, that's great. What is the difference between displacement in letter A versus distance traveled in letter B? So what's the difference there? Vivian? Certainly. So in order to find the distance traveled, right, any directional movement towards the left needs to be counted as a positive contribution towards the distance traveled versus displacement, it was counted as a negative contribution. So how do we remedy that? Well, analytically, I think it's easiest to go ahead and consider closed interval method and consider my magnitude of the change in between, right, in between critical values and my endpoints, and then summing those up, as opposed to doing the absolute value and breaking up into separate definite integrals. The choice is yours. I'm going to go ahead and start with my v of t, which was given by t squared plus 3t minus 4. And I'm going to determine, right, when my particle, right, switches direction, moves to the right versus moving to the left, so that I can count each of those subintervals as a positive contribution. So I'll go ahead and set this equal to 0 if I'm doing this analytically solve. So let's factor first to fail. We'll break that up into a product of two binomials and our expert resident factor, Riley.
T plus 1 or plus 2. No, yes. And minus plus 2? No, minus 2. Minus 2.
All right, let's check. Outside product of minus 2t, inside product of plus 2t, sums to not 3t. Oh, what's my other integer pair factor choices for the last -4? Let's see. Well, -4 is product of integers 1 and 4 or 2 and 2. We just saw 2 and 2 failed miserably. So what about 1 and 4?
Minus 1 plus 4.
Minus 1 plus 4. Raise your hand if you have the same factorization as our expert method factor. Yes, that's right. And we can pin down the values of t then by setting each individual factor equal to 0 and solving. So it looks like analytically we've determined that time t equals -4, the particle is stopped. Well, for us that doesn't have meaning, right? Because we're looking on the interval 0 to 2 and we can't go back in time. Also that we can say what? Well, let's go ahead and throw those. Let's go ahead and throw those endpoint of my interval values, 0 and 2, on a time, all right, position function number line, along with any critical values where the particle is stopped and could change direction. So it looks like we need the 1. That's what that was for. And so what are we doing? We're going to go ahead and evaluate my position function at the associated time values. Remember, this position function, we don't have an initial condition. We can't pin down that plus c, but we can still use Courtney's, right? Without the plus c or with the plus c, and the distance traveled will still be the difference between those ending points. So I'll still use Courtney's t. Oh gosh, I forget t cubed over 3 plus 3 halves t squared. Was it plus?
Yeah.
Plus 3 halves t squared, and then it was minus 4t. Minus 4t. Oh gosh. Oh, that's tight. It's going to work out perfectly. So let's go ahead and evaluate. 0 in. Ah, I got that one. 1 in 1/3 plus 3 halves minus 4. I bet we can do that. So that would be sixths for a common denominator. So 2 sixths plus 9 sixths is 11 sixths. Minus 4 would be minus 24 sixths. 11 sixths minus 24 sixths. Negative 13 sixths. Woo! And 2 8/3. And we already did this 8/3 plus 6 minus 2. So we already did that. And we got 8/3 minus 6 plus 2, 2/3. Looks like 2/3. Great. Who cares? Well, because now we can count even direction motion, right? Whether I'm traveling to the left or to the right as a positive contribution. How much did we change on this first subinterval? Looks like we changed 13 sixths, right? Positive contribution. And how much did we change on the second interval? From negative 13 sixths to positive 2/3 is 4 sixths. Look like that's 13 4 17 sixths. Put it all together. What do you have? Hot cross buns. No, we've got 13 6 plus 17 6 is a whopping 36, which is so nice. Isn't that just 5 units? Raise your hand if you have that. 5 units? 5 units? Yes! That's great news. And let's go ahead and, the moment you've all been waiting for. Yes, that's right. The verify numerically slide, where in general our displacement is given by the integral from a to b of v of t dt versus our distance traveled is given by the integral from a to b of absolute value of v of t, we're being told us with respect to time. And we'll do both of those numerically. What do we mean numerically? That means using the built-in capabilities of our graph. So for my y equals, I'll put in which function? Well, we want to put in our velocity v of t. So for velocity, we're using t squared plus 3t minus 4 home screen. We're doing math 9. And we're going from 0 to 2 of vars y vars function y1 with respect to x, and it looks like our displacement is 0.6667. Ah, yes, indeed. Math rack, math rack, math rack. we get the 2/3 that we already got, so that's good news. And one to go, our distance traveled, we can do the same thing but include our absolute value bars. So I'm going to try it again. I try it every time. And we'll go in and we'll try to do second insert math num abs. Oh, wow, that was a good try. It was fun anyhow. Thank you, come again. How's that? Better? That's my horror, no? We win. Math works. It's so gratifying, isn't it? Alright, what questions do you guys have about our displacement versus distance traveled? So on your test next class, you'd be expected to have this on either, right, portion, the non-calculator, or the calculator allowed, right? We can perform our analysis without the use of the graphing calculator, and if we do have a calculator, then you just have to write this down with the appropriate limits and function, right? And then after you've shown this, you can go to the Math 9. Cool? Great. All right, let's go ahead and take care of our OTL number 6 check, and I'll pause the recording. Okay, ladies and gentlemen, as we continue our tour of assorted applications from definite integration, today we're going to work it out. What? Working it out. In the traditional sense, we may consider work to refer to the amount of energy it takes to get something done. Like, I don't like polynomial long division. It's too much work. Or, that last OTL was a lot of work. Yes? In the mathematical sense, though, work happens when we exert some force, right, over a distance. And so, when a constant force F is exerted through a distance d, then the work W is given by force times distance. And there's a variety of real-world applications for that. Today we're going to look at a couple, and then you're going to have an opportunity to review as you gear up for your test on Tuesday. I've included two forms here for constant force exerted over a distance d, because the main units that we use, and you can use a variety of units, but the main units you see are SI units. When we're talking about force measured in newtons, and distance d measured in meters. Then our work, Newton meters, gets its own unit, and that's called a joule. And that's like an energy. You'll notice from your chemistry and from your physics that a joule, right, is a measurement of energy, right, of units that are energy. Well, that makes sense. It takes energy to perform work, right, both in the mathematical sense and the exertion sense, physical or mental exertion. All right, so joules, there, I think I wrote on the closer. So newtons and meters. We could also measure work in the traditional British units, and so here we have our force measured in pounds. So that's like already a weight that already takes into account our gravitational acceleration, just like newtons take kilograms per meters per second squared. Well, here we have our pounds, and then our distance will be measured in feet, and we get the incredibly complex unit for work, foot-pounds. There. And we'll go ahead and work, and we'll do an example with each today. Okay, so we've got joules. Do I need to write that out? Joules, newtons, and pounds, feet, foot-pounds. Ready? All right. So let's suppose that a force of 28 newtons, and these first examples are simple, so you don't have your own printout, but you can do it right up there with those two equations. The force of 28 newtons is required to push a cart laden with calculus texts. How much work is done moving the cart 3 meters from Grace's desk to Tyler's? Just for some light reading. Well, is it a constant force exerted over the course of a distance d? It's nothing, right? It's nothing harder than a product of my force times distance. So I know in general I can start with my equation. Work W is given by my force exerted through a distance d. In this case, the force exerted is a constant force of 28 newtons, and that is going to be exerted through a distance of 3 meters. my units work. So I've got newtons times meters is joules, and so it looks like the work required here would be 28,390 less 6 is 84 joules. 84 joules is that easy. Okay. Oh, British units you say? How much work is required to lift our 8-pound calculus book 3.5 feet from the floor to the desktop, which is now looking more like 3.25 feet. That's zero. I was at home. I couldn't see a desk from home. So how much work is required to lift our 8-pound calculus book 3.5 feet from the floor to the desktop? So we're exerting a constant force, right, in the opposite direction of gravity. The pounds already takes that weight into account, so we're okay with our force there. So that'll be a force times the distance, and so W equals force times distance. In this case, it's 8 pounds times the distance of 3.5 feet. So this would be 8 times 3 is 24, plus another half of 8 is 4 is 28. Is that 28? And this is pound feet. Oh, that's the original. Okay. If only life were so simple, right? Do we always have a constant force exerted over the course of my entire interval? No. Oftentimes when we're pushing the roller cart, right, we'll slow down, then the cart slows down, we gotta push it up again, and then we have to stop, we have to talk, right, with Mr. Aker, and then we keep going, and so on and so forth. And so oftentimes we're not dealing with a constant force exerted over the course of my distance. Oftentimes we're dealing with a variable force, and that's what we're after with calculus. So what happens when the force required to move the object varies over the distance traveled? Well, let's suppose that, right, we were to take a look at, just a small distance that we push, right, that cart, call it delta x. If we multiplied that force that was exerted at that particular time, multiplied by the distance, right, that we push, and then sum up all of those little elements of work, when we get the total energy expended, right, in the course of the push down the hallway, well, that's exactly what we've done with, in the context of summing up infinitely thin rectangle areas to get the area of irregular shaped region, or summing up infinitely thin disks, right, with a small volume, like a quarter, to get the entire volume of a solid. Now we're going to do the same thing. We're going to sum up infinite number of small exertions of work and get the total work done over the course of my interval. So when a variable force given by the function f of x, so it could change now over my interval, is exerted over an interval a to b, then the work w is given by the integral from a to b of f of x, where f of x is my force function, times dx. And again, you can think about this, right? You can think about this definite integral as a product, right? A product of integrand variable values multiplied by independent variable values. And we've kind of talked about that time and time again. If we are measuring this in newtons, and if we're measuring my distance, right, traveled in meters, then it works out and we still get joules, right? We still get joules for that calculation. So above all, right, a definite integral is a quantity, and it represents a product of my integrand function variable value units multiplied by my independent variable value units. All right, so let's go ahead and do something. So a rock climber is about to haul up 100 newtons of equipment that has been hanging beneath her on 40 meters of rope weighing 0.8 newtons per meter. How much work will it take to lift? First, we'll do the equipment. Okay, so let's consider what's going on here. So a rock climber is about to haul up 100 newtons of equipment that's been hanging beneath her on 40 meters of rope weighing 0.8 newtons per meter. How much work will it take to lift the equipment? All right, so the equipment, right, the equipment we're saying is 100 newtons, and that's packed up in our haul bag, right? So let's break this up into pieces and just consider not the rope, right, not the pulleys. Let's just think about the bag of equipment itself. Is a constant force, right, required to move that 100 newtons up. Yep, right. Equal and opposite from gravity, we're going to exert a constant force. So for this first part, the equipment, we can simply use my constant force equation for work done is given by the force exerted over the length of the distance of that exertion. So the work done for just the equipment is, you guessed it, 100 newtons applied over a distance of what? How far are we lifting? 40 meters. Do my units match? 100 newtons times 40 meters is Newton meters, and that's my joules. So yes, that works well. So the work done, did I do 40? Yeah, I did. So the work done for just this part is 4,000 joules. Is that right? 4,000 joules? Cool. All right. But that is only the equipment in the haul bag, right? We still need to take into account this rope. And it requires work to lift the rope itself because that has, right? That has mass. And in fact, it weighs 0.8 newtons per meter. So how are we going to consider the rope? Well, is the rope, right? Does the rope require a constant force to exert throughout the course of the 40 meters? Yes? No? I'm getting yeses and I'm getting no's. Why are you thinking no, Kobe?
Because if you're pulling the rope, you only have to pull however much is hanging underneath.
Yeah, absolutely. And so, in the beginning, you're pulling 40 meters worth of that rope up. It's going to weigh more, right? Because you're lifting more rope. Then, as you get towards the end, there's less and less rope in. Well, it'll be easier to pull up. You'll require less force, right? As that you get towards the end, right, of your distance that you're pulling the rope through. So, is this constant or variable force? This one is variable force. So, we're not going to take our simple equation, W equals F times D. Now we have to consider our definite integral, where the work required is the definite integral from A to B of a force function that varies. Call it F of X with respect to X. All right, so we need to generate our force function. And we can think about this a couple different ways. One way, we draw a little clip here. So we've got our rock climber, and she's going to lift. She's going to lift the haul bag with the rope. A distance of 40 is the whole thing. If we let a portion of that be X units, and the whole thing be 40, where should I put that? Meters, sorry, 40 meters. Can we write a variable force function that represents the force or the weight of the rope at a given distance X into the in the course of the hauling? Well, yeah, right. If 0 meters have been hauled in, that would be we're all the way at the bottom. How much force, right, would be required? Well, we know that my rope weighs 0.8 newtons per meter, so I can generate a linear function where if 0 meters have been hauled in, the rope weighs 0.8 times 0.8 newtons per meter times 40 meters. So how much does the rope weigh when 0 meters have been hauled in at the very start? What's that? 320? 32. That's 32? You can do it. Are you ready? Open on your teacher. 32?
Yeah, 32.
Awesome, thanks. At the end of the problem, right, if you were to have 40 feet hauled in, 40 meters hauled in, then how much would the rope be weighing? Well, we'd be down to 0 because it would be done through the hauling process. This way we could model, right? We could model that variable force required to lift the rope as a linear function that connects those 2 points. Now, you can do this lots of different ways. In fact, we'll find out the slope here ends up being the 0.8 newtons per meter. Let's see. My rate of change in the force required with respect to the distance of my haul is given by y2 minus y1 all over x2 minus x1, which equals negative 8/4, negative 4/5, which equals, you guessed it, negative 0.8. So if we set up our x to represent the number of meters into my haul, then my force function will be given by f of x equals starting force 32 newtons minus decreasing at a rate of 0.8 newtons per meter x cubed. And when I'm all the way at the 40, then I'm down to 0 newtons required to haul. Let's do it. So we'll integrate from what to what? Well, it starts out with how many meters into my haul? 0 meters. And concludes with how many meters into the haul? 40. Sorry, I should probably say work equals variable force function times dx. So my variable force function we decided was 32 minus 0.8 x dx. Now, depending upon where this is, yeah, we can integrate this easily. It's a linear function. But we're going to go with our calculator aloud and just math 9 it in the interest of time. Math 9, I'm going to go from 0 to 40. My variable force function was 32 minus 0.8x with respect to x. Looks like 640 joules are required to haul the rope alone. So put it all together, and what do we have? We've got the rope and the equipment, so we just saw the rope was 640 joules required, plus our equipment. Was that the 4,000? Was that 4,000? Hey, nice. Gives us 3640 joules. So a key to completing these work problems is being able to separate which quantities require a constant force exerted versus which quantities require a variable force exerted. Yes? All right, let's consider another. What questions do you have on this first one? The rock climber one? All right, let's take a look at another then. So a cable that weighs 2 pound-feet, no, 2 pounds per foot, very different. So a cable that weighs 2 pounds per foot is used to lift 800 pounds of coal up a mine shaft 500 feet deep. Find the work done. So can everybody picture what's going on here? We've got a cable that's lifting a quantity of coal up a mine shaft. 800 pounds of coal need to be lifted, but the cable itself has mass, right, and requires force to lift. So let's break this up into pieces. Which part of this requires a constant force to be exerted over the course of the 500-foot distance? Right, which part of this? Is anything constant here? Fill it with P. The coal, right? So the coal's mass is not changing, so the force required to lift the coal only, right, is a constant force required. Therefore, we can break that up into our first equation. The constant force required we'll do for the coal. So for the coal, we're constant. Yay! We know then the work required for the coal is given by the force required to lift the coal exerted through the distance. All right? So for us, it's 800 pounds. Well, that is a force. That's already taken into account a weight, so that's a force. So 800 times the distance of the mine shaft was 500. So it looks like the work required to lift just the coal up is, goodness gracious, 40, and then 1, 2, 3, 4. Are you guys getting 400,000 joules? The zang. Okay. Nope, it's not joules. It's 800 pounds times the distance of 500 feet is pound feet. Those Brits. Foot pounds. Sorry, thanks, Brittany. Foot pounds. I don't know if I need the S or not. We're going SI, aren't we? We're going SI anyhow. Never! Alright. What else do we have? We always have coal. We have the cable. Well, is the cable going to require a constant force to lift it or a variable force? The cable. The cable is going to be a variable force. When all the cable's out, it will take more force to lift it, versus all the cables in is going to take less. And so we need to write a force function, right? It gives the force required as a function of the distance out, or the distance, right, remaining to be hauled, or the distance hauled so far. And we can do this all different ways. So if you want to keep it like the same scheme as the rock climber, we could again let the distance hauled so far if I let x equal the distance hauled so far, then the force required when 0 feet have been hauled would be, oh gosh, 2 pounds per feet times the 500 feet would be 1,000. Right? I need 1,000 foot-pounds of force through all the way 500 feet I'm hauled. Then I would be down to, right, 0 force required because it'll all be at the top. Right, all that so that I can get my linear equation. It looks like my variable force F is given by initial value 1,000 foot-pounds minus, and it looks like down 1,000 over 500 is negative 2x. Well, look, you guys, we already had that from our, right, from our weight originally. All right, now we're ready for our deck. So our variable, our work done from the cable. That's unfortunate. CO for coal and CA for cable. I'm like, I was going to use W sub C for, the work from the cable. Oh, very good work from the coal. All right, no problem. Ain't no hill for a stepper. From 0 feet hauled all the way through 500 feet hauled of my variable force function, 1,000 minus 2x dx, I'm going to get, again, this will be easy to integrate by hand, 0 to 500, but math 9 is so much fun. And my variable force, 1,000 minus 2x, close, with respect to x. See how we did. Looks like 250 foot-pounds. Zang. Nope, 250,000 foot-pounds. Okay, so then we've got that, so we need the total. So the total work done. Looks looks like our 400,000 plus our 250,000 is 650,000 foot-pounds. Yikes. Better start working out. Sydney, keep it down. Sorry. All right, guys. The work done W in joules by a constant force F in newtons exerted over a distance d meters is given by the equation. The work done W in joules by a variable force, call it F of x in newtons, exerted over an interval a to b in meters is given by the definite integral. Did you guys want to get this? Oh. That's what I get when I'm working in the morning. Doesn't get to the copy. That's all right. The last part will be easy. It'll be oral. It'll be an oral closure. All right. So for constant force exerted through a distance d, then what's my work done as an equation, Danny?
Work equals force times distance.
Cheesy. Very nice. Variable force F of x, right? The work done is given by Tyler.
Work equals integral from A to B
Oral closure. Given a particle's velocity v of t, write an expression for each of the following over an interval. All right, tell the class an expression for displacement given v of t. Vivian?
Displacement equals
Thank you. Distance traveled. Marissa?
The integral from A to B of the absolute value of A to T. There.
Thank you. If f, gosh, it keeps going. It's like the never-ending closure. If f of x is continuous and differentiable on A to B, then the function's exact length L over the interval, you thought it was going away. No, it's here to stay. It is given by L equals. So this is exact length would be given by what expression? Riley.
Is it, okay, so it's the integral from A to B of, is it absolute value?
Oh.
No, square root. Okay, it's something squared. The whole thing's squared, I think, yeah. There you go.
We'll just go piece by piece, no problem. Your number. Yes. I'm just gonna leave a little bit of space. I'm gonna leave a little bit of space right there. Yes, for that, and
dx.
oh god. That took a lot of work. Absolutely. Good job, you guys. So you have to know all this stuff on our review day. And we've got OTL, but I have them picked out now. I just need to write them down. So I'll go ahead and stop the recording and then share with you the OTL exercises.